This video is about solving trigonometric equations using identities or multiples. As always, begin by reading carefully through the textbook and taking some good notes, but now consider the following highlights for this topic. We're going to begin by recalling several items. First of all, the zero product property and factoring methods from algebra, and we've done this in recent topics. Hopefully you've been tracking along with that. If needed, go back and review some more of that. Secondly, we're going to recall unit circle values in basic trigonometric equations. Again, in previous topics, we've been doing that. Thirdly, we're going to recall trigonometric identities. Now, this has been really several previous topics, and by now there's quite a body of them that we have to have memorized. There's a couple that we don't have to, as noted in those lessons, but most of them involve quite a bit of memory. Furthermore, with all the unit circle values, at this point, you have quite a few things that you should be able to hopefully write out by memory, and it's good practice to do this routinely. So take out a blank sheet of paper, draw the full unit circle with all of the values we have on it. Also write out all the identities from nothing, from memory. And if you can do that routinely, they'll stay fresh in your memory, and then you'll be able to do a quick brain dump at the start of an exam so that you can have those readily available next to you. Not have to worry too much while you're trying to do the questions on the exam. Now, what we're going to do next is solve trigonometric equations involving functions of multiples of angles. And you'll see what that looks like in a short minute here. We'll first solve the multiple of the angle, then divide to solve for the angle. Again, you'll see examples here shortly of what this looks like. And then an additional note would be as follows. If we square both sides of an equation in the solving process, we must check for extraneous solutions. You may recall extraneous solutions from algebra where you get a solution, or at least you think it's a solution, but then when plugging it back into the original equation, it doesn't actually verify that it works. It might cause some kind of undefined situation or show that both sides are not actually equal. We got to check situations when we square both sides of an equation, which we may need to do, as you'll see shortly. Let's take a look at some examples where we want to solve the given equation. And the first of those given is cosine of 2 theta, that's on the left side, equals 3 sine theta minus 1. And that's on the right side. Now we want to solve the equation, and as we've been seeing recently, sometimes that involves factoring or just using the unit circle to be able to identify some of our basic functions. However, in this case, I want you to notice one thing. That is, you have two different trigonometric functions involved. You see, we've seen situations where maybe you have like a sine squared and then a sine term in the same equation, and we've been able to factor. But in this one, you'll notice the way it begins, we have a cosine of 2x and a 3 sine, theta. It's cosine 2 theta and 3 sine theta. We basically have two different trig functions, cosine and sine, which means we're not going to be able to get those in a place where we can factor unless we use an identity to replace cosine 2 theta. Now, you may recall from all these recent identities that we have some options for that. So let's bring back what we might need. Now, there are 3 different options for cosine 2 theta. You may recall you could do cosine squared theta minus sine squared theta. You could do 1 minus 2 sine squared theta, or you could do 2 cosine squared theta minus 1. Well, we want something where we can get some kind of quadratic looking equation that involves sine, which we already have. So what I'm going to say or suggest is this. We know that cosine of 2 theta could be written as something that involves a sine squared of theta. That's the goal. Can we get something involving a sine squared? Now you may notice if you look at the list, there are actually a couple options, but we want it only involving sine squared, not even a cosine. So what I'm going to suggest, you'll see how this works soon here, but let's use the form of this identity where we say cosine 2 theta equals 1 minus 2 sine squared theta. Now, watch what happens when we replace cosine 2 theta with that. We'll say it as follows. 1 minus 2 sine squared theta, there's the direct replacement, equals, now on the right side we'll still have the 3 sine theta minus 1. That's just the original right side. But notice here now we have a squared sine and a single sine. This is maybe motivation to say, hey, if we get this in a quadratic looking situation, we might be able to factor and solve. So I'm going to get the squared sign onto the right side so that it's positive. To do that, we'll do two things. We'll subtract 1 and we'll add 2 sine squared theta to both sides. So we'll subtract 1 and add 2 sine squared theta on the right side as well. That leaves nothing on the left side except 0. So let's rewrite this all. We have 0 on the left side now equals. On the right side, we'll have 2 sine squared theta. And I'm going to write this in descending order. That was the term we just added over there, and it's positive. So really it's a positive or plus 2 sine squared theta. Then in descending order, next we'd have plus 3 sine theta. When I say descending order, I mean we have a sine squared first, then we have a single sine, and then the last term would just be the constants. We had a negative 1, we subtracted 1 more, so altogether we'd have a minus 2. Notice now it's in descending order, and if you put it into the algebraic form like we were doing when we were introducing this topic previously, this is kind of like the 2a squared plus 3a minus 2 setup, which is just a quadratic that we can factor. So we're going to stick this time with just the trig. If you still feel comfortable using or doing the algebra with just like a substitute value or letter a, that's fine. But I'm just going to jump in here to say if we were to factor 2a squared minus 3a, 2a squared plus 3a minus 2, we'd end up with a 2a and an a in front. So we'll call that a 2 sine theta and then a sine theta, each in the front of those parentheses now where we're factoring. So we have 0 equals a set of parentheses that has 2 sine theta and then a blank, and then another set of parentheses that has sine theta and then a blank. We need to fill in those blanks knowing that last times last, if you're foiling, has to become negative 2. But then if I combine the outers and the inners, I have to get the middle term of positive 3 sine theta. So if you want to pause and just kind of mess around with the factoring a little bit on that, that's probably a good idea to make sure you get these terms correct. Hopefully you're getting something like 2 sine theta minus 1 and then sine theta plus 2. I believe those will work. You can double check it always by foiling or multiplying those together. Now, in this situation, notice we have a product equal to 0. This is where we can use the zero product property. We've done this many times by now. So we can say that one of our factors, I'll just pick on the first one, 2 sine theta minus 1 equals 0. Well, that would mean if I solve for sine theta, by, of course, adding 1 and then dividing by 2, I'd have sine theta equals positive 1/2. If I take the other factor and solve it, if it's equal to 0, I would be subtracting 2 from both sides. This would give us then sine theta equals negative 2, but as we know from the range of sine, that's not a possibility. The lowest sine goes is negative 1. So that means we're not going to get a solution from that branch. You can just ignore it. But the first one is something familiar to us. In fact, that's even a nice unit circle value. Sine theta does equal 1/2 on the unit circle. Let's just recall where. And again, you might want to have your unit circle handy or close by. You'll recall that sine theta is positive 1/2 in quadrants 1 and 2, and it's actually the first or lowest, you could say, marking in each of those quadrants, right? Out of the 3 markings that you have in any quadrant, the first or the lowest in quadrants 1 and 2, I guess it's, if you're going counterclockwise, it's the first in quadrant 1, it's the last one in quadrant 2. But those lowest or closest to the x-axis places, those are where sine is 1/2 vertically speaking. So what we need to know is where those are in terms of arcs or angles. If you're going from the starting place of 1, 0 on the right side to get to the first marking in quadrant 1, of course, that's where theta would equal pi over 6. That's our first special angle or special arc. And then to go from the starting place all the way around to the second place in quadrant 2, this is where theta would be 5 pi over 6. Again, just going back to unit circle values. So we have two potential solutions here, but we want to represent all the solutions, which means we're going to do as we've been doing, where we add multiples of the period of this function. Now, we also want to pay attention to whether doing this to one of them will produce the second one or overlap with it. If I take pi over 6 and I add a multiple of the period, which is 2 pi, so I do 2k pi. We've been seeing this where k is an integer known as a script z usually. Okay, so k is just some integer value, meaning if I do 2 times k times pi, that's a multiple of 2 pi, where k is positive or negative. That's what it means to be an integer. So this will go any number of times around the circle, one more full time from that place. So I can go around one more time or 2 more times or whatever it takes. The point is every time you go another lap around the circle, you get back to the same place, which gives you another solution to this equation. Now, if we do that, notice that will not actually hit the other location, the 5 pi over 6. If I start at pi over 6 and add another lap, meaning 2 pi, that takes me back to the same place, but that does not stop at the other solution we're identifying here. So we're going to have to represent the other one as its own set of repeated solutions, 5 pi over 6 plus 2k pi, same kind of thing. So now we have the two original solutions we had started with within one circle. That was the pi over 6 and 5 pi over 6. That's where we had to know the unit circle and which places on it will produce the sign value of 1/2. But we identified those and then represented all the other infinite places we could find another solution with the 2k pi. All right, moving on to example number 2. This one begins as follows. The left side is sine theta minus 1, and that's equal to the right side, which is cosine theta. And of course, our goal is to solve this for theta. Now, sometimes you need to see a strategy or a method used so that you can maybe recall it and have it in mind the next time you might need to use it. This might be one of those problems where if I try something here and show you a method, you may say, well, I wouldn't have thought of that myself, but now that I see it, okay, I might be able to catch that again. That's fine. That's sometimes the way we understand and learn math. So what I'm going to suggest here is a strategy where we rearrange this by, I'm going to move the cosine that's on the right side over to the left side. I'm going to move the -1 that's on the left side over to the right side. So just rearranging here, this will turn into sine theta minus cosine theta on the left side, and that equals 1 on the right side. Again, just do some algebraic rearranging there. Now, if you don't know why that might work, just stay tuned and know that if you see it this once, you might catch it again the next time you need it. Let's then use a method called squaring both sides of the equation here. If we do this, you'll notice what happens. On the left side, you have sine theta minus cosine theta, which is really a two-term expression in parentheses. If I square it, really that means I'm going to be FOILing this out. So to FOIL out sine theta minus cosine theta, first times first would be sine, 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 or sine squared theta. Outers and inners would produce -2 sine theta cosine theta. And then last times last would be plus cosine squared theta. And that would all be equal to 1. The right side is just 1 squared, which is 1. All right, so if these foiling details are troublesome to you, write it out slowly, ask questions about it. But that's just an algebraic step there we're using to FOIL that out. Now let's recall an identity we might want here. So I'm going to say this on the side, recall our Pythagorean identity, which is by now it's kind of old news for us, but we know that the Pythagorean identity says sine squared of whatever, I'll just use x, sine squared of x plus cosine squared of x equals what? That's right, 1. So if I look at the left side of my equation, you'll notice there's a sine squared theta plus a cosine squared theta, which means we could represent both of those terms as combined equal to just 1. It doesn't matter whether it's an x or a theta or an a or a w, whatever the variable is, doesn't matter. The Pythagorean identity still stands. So we can just represent those two terms combined as the number 1, which means we really have on the left side here 1 minus 2 sine theta cosine theta, which was just that term already at the previous step. And that equals now 1. We had a 1 on the right side. We haven't touched it yet. But now if I subtract 1 from both sides, you'll notice then they cancel on each side, giving us a negative 2 sine theta cosine theta equals 0, which is fairly convenient, but still maybe a little bit elusive, like not sure exactly where to go next. So let's try some more. What if we divided by negative 2 on both sides? Notice then the negative 2's would cancel on the left side. On the right side, we'd have just 0 over negative 2, which is 0. So let me bring this up and redraw this. We have really just a sine theta cosine theta equals 0. If we now use the zero product property with this, which is applicable because we have a product that is sine theta times cosine theta equal to 0. So if I set each of those factors, one being sine theta and one being cosine theta, equal to 0, which is exactly what the zero product property would indicate, then we get several values for theta. We're wondering, where does sine theta equal 0? Well, think of our unit circle, right? Sine theta is the y-coordinate. Where is that 0? Basically on each side of the unit circle, left side, right side. Those places would be 0 and pi in terms of radians. Or secondly, where does cosine theta equal 0? Well, that's where the x-coordinate is 0, which would be the top or the bottom, which would be then where theta equals pi over 2 at the top or 3 pi over 2 at the bottom. So we actually have 4 different places where these are true. That is where sine theta equals 0 or where cosine theta equals 0, which gives us 4 solutions within one wrap of the circle. Now you'll recall near the beginning we squared both sides of the equation to get us something better to work with. What that means, as we noted above in our notes, is that we're going to have to check for extraneous solutions. Now what does that mean? That means we're going to take every one of these solutions we think we have, 0, pi, pi over 2, and 3 pi over 2, and plug them each back into the original equation to see if indeed they make it true. So I mean, just like that, if you take theta as 0 and plug it back in, 0 for theta would mean sine of 0 minus 1 equals cosine of 0. Well, sine of 0 is 0, so 0 minus 1 is negative 1. Does that equal cosine of 0? Actually, no, it doesn't. So we have to exclude some of these solutions because they're not actually valid. They're called extraneous. So 0 doesn't work. Let's check pi. I'm just plugging them back in the original equation. Is the sine of pi minus 1? Well, let's see. Sine of pi would be 0 minus 1 is negative 1 equal to the cosine of pi. Cosine of pi is negative 1. Actually, yeah, that works fine. So pi works out just fine. We'll check that one off. Moving on to our other set, we had pi over 2. Pi over 2 when plugged in, let's see, sine of pi over 2 is 1, minus 1 is 0. Cosine of pi over 2 is 0. Actually, that works fine too. So pi over 2 is good. Let's check 3 pi over 2. Plugging it in, sine of 3 pi over 2 is negative 1. Negative 1 minus 1 is negative 2. Cosine of 3 pi over 2 is not negative 2, it's 0. So actually, 3 pi over 2 does not work. Those are called extraneous. That is the pi and 3 pi over 2. No, I'm sorry, 0 and 3 pi over 2. The two that we had to exclude or cross off, those are called extraneous, which means we don't use them for our solution. So we'll write our solution in its infinite form with the k and all that stuff without those. So we're going to say our solution here is theta equals pi I'm just picking on the first one I wrote left to right. You could pick either one first. Pi plus, now if we're looking at this original equation with sine and cosine, notice the period of those is each 2 pi. So we'll say plus 2k pi to represent any other lap around the circle starting from the solution of pi we already found. And then similarly, theta could equal pi over 2, the other solution we found that works, plus any other lap around the circle, so plus 2k pi. So those are the two ways we could represent all the infinitely many solutions to this equation. All right, let's move on to our third example. This one reads as follows. It says, find all solutions, then find the solutions in the interval from 0 to 2 pi, where 0 is included but 2 pi is not. So basically within one full circle is what that means. For the following equation, we have square root of 3 tangent 3 theta plus 1 equals 0. So on the left side, we have this square root of 3 times the tangent of 3 theta plus 1 equals 0. Now, in order to solve this equation, we want to find all the solutions, and then we want to find the ones that are only within one wrap of circle, which almost seems to be in reverse from the way we've been doing these problems. It can seem like that, but it really doesn't look too much different in the end. So what we're going to do is start with the equation given. I'm just going to copy this down. We had square root of 3 times the tangent of 3 theta, but that's like all the input of the tangent. The 3 theta, you could put it in parentheses after the tangent to make that super clear, and then plus 1, and then equals 0. Now, in order to solve this, like we've been doing, the first step is to get the trig function by itself. So we'll start by subtracting 1 from both sides. Just some basic algebra here. This means we have square root of 3 times tangent of 3 theta equals negative 1. And then we can divide both sides by the square root of 3 as another step in getting the trig function by itself. So now we have tangent of 3 theta on the left side equals negative 1 over the square root of 3, which it would be more familiar to us if we rationalized. That's the same thing as negative square root of 3 over 3, which is, again, just more familiar with our unit circle. Speaking of which, let's go ahead and draw one. Let's get a little circle here because I think we're going to have to remember the key places for tangent, which we wrote a few topics ago. You may want to recall. We have, for tangent, all the way around the unit circle. Hopefully you'll have these memorized by now or getting close. What the values are for tangent, we care about where it's negative root 3 over 3. Now, negative would be quadrants 2 or 4 for tangent. Remember, tangent is sine over cosine. So we're looking at quadrants 2 or 4 for where tangent is negative. And then you may recall also that the places where it's divided by 3, the root 3 over 3, that's where it's closer to the x-axis. So that would be, if you're going counterclockwise around the circle from the normal starting place on the right side, you're going into quadrant 2 to the third marking in quadrant 2. Or in quadrant 4, you'll also get a value for negative root 3 over 3 for tangent in the last place. So that would be like starting at the starting place and going all the way around, almost fully around, but there's one more left over place. The last place in quadrant 4 if you're going around counterclockwise. So we have two places where this can occur. However, notice here that we have not just theta, but 3 theta. This is where the multiples of angles is coming in to play with our title and our notes above. So what we're going to say here is that we know where those places are from the unit circle, but what we have now is that 3 theta is really equal to them. So we'll say it algebraically like this. 3 theta would equal, actually I'm going to write this directly next to the circle. So we got 3 theta equal to the first place you'd come to. I'll just go in order, counterclockwise here. The first place in quadrant 2, that would be 5 pi over 6. So we'll say 3 theta equals 5 pi over 6. 3 theta is just the angle we're using that was given inside the tangent function. Our job is to get it down to theta next, but we're getting there, okay? So 3 theta could be 5 pi over 6. That was the place in quadrant 2. But then in quadrant 4, that was 11 pi over 6. That means 3 theta could also be 11 pi over 6. So we have both of those places now marked from the circle. We're setting our angle, our multiple angle 3 pi equal to them. Remember how we did the infinitely many solutions? Well, here's how. We're going to do this again the same kind of way. I'm going to write these out again. 3 theta would equal, the first one was 5 pi over 6, but then we would normally say plus, now remember the period of tangent is just pi, so we'd normally say plus k pi. But notice here for a second, since the period of tangent is really pi, the second solution we got, the 11 pi over 6, would actually be included in the way we represented our first solution, but going on forever. So 5 pi over 6 plus k pi would include 11 pi over 6. Why? Because if k is 1, then 5 pi over 6 plus 1 pi, which is also known as 6 pi over 6, would give you 11 pi over 6. So since 11 pi over 6 is included in the first representation we wrote, we don't need to write another one that would be, for example, like 11 pi over 6 plus k pi. It's already being represented, and if we just keep going multiples of pi around, we're going to hit every single solution we might need. So that's so far pretty familiar to us based on things we've been doing in recent topics. What's new here is that we really want theta, not 3 theta. So what we'll do is simply a little bit of algebra here, and we're going to, in this case, multiply, or actually divide by 3. You could say multiply by 1/3 on both sides. Same thing as dividing by 3. But that will do what we need to get theta alone. So if I divide the left side of our equation, which currently reads 3 theta equals 5 pi over 6 plus k pi. If I divide the left side by 3, then those 3's cancel. If I multiply the right side by 1/3, also known as dividing that by 3, then the result we get overall would be just a theta on the left side. If I distribute the 1/3 into both terms, then 5 pi over 6 times 1/3 would be 5 pi over 18, because 6 times 3 is 18. You'd be multiplying denominator with denominator there. Plus, and then for the second term, we'd have k pi over 3. That's just as written, k pi over 3. You could say k over 3 times pi, same kind of thing. So this represents any solution, again, for k being an integer. Hopefully by now you're getting used to this. A script z means integers. So we have theta equals 5 pi over 18 plus 1/3 k pi, or k pi over 3. That's for any integer k, and this represents all the infinitely many solutions we have to this. But then this problem said, then find the solutions in the interval 0 to 2 pi. So let's now do this. I'm going to color coordinate this with something different. So 0 to 2 pi will do in its own color. And in that case, we're going to just start with the first one possible and keep incrementing k until we reach a point where we're within this one full circle. So let's do it this way. We'll say theta equals, the first one was where k would be 0. Just kind of note that here. So if k is 0, then theta is really just 5 pi over 18, right? Because if k is 0, then the second term becomes 0 over 3, which is 0. So really it's just 5 pi over 18 if k is 0. Well, what if k equals 1? Well, now you're plugging in 1 for k, which will give us a solution of 5 pi over 18 plus 1 pi over 3. Or in other words, 5 pi over 18 plus pi over 3. That's if k is 1. Let's say they wanted how many of these? All of them within the first wrap of the circle. So let's kind of double check this. 5 pi over 18, that's a little bit less than 1/3 of a pi. Certainly that's within one full circle. The next one, it may be helpful to combine these fractions, right? Pi over 3 in terms of 18 would be 6 pi over 18. So I'm going to write it that way just to get a common denominator there. which means you're really looking at 5 pi over 18 plus 6 pi over 18, which is 11 pi over 18. So we have 5 pi over 18 for the first, 11 pi over 18 for the second. Are we still within one wrap of the circle between 0 and pi over 2? Yes, because we're certainly less than 2 pi so far with 11 pi over 18, right? Let's keep going. What about if k is 2? Well, that would be 5 pi over 18 plus 2 pi over 3. But again, if we use a common denominator here, I could multiply top and bottom of this 2/3 fraction by 6 to get an 18 denominator. That would give us 12 pi over 18. 5 pi over 18 plus 12 pi over 18 would be 17 pi over 18. But 17/18 is still, it's even less than 1. So we have plenty of room here. That so far is also within one circle. What about when k is 3? Okay, this would be 5 pi over 18 plus 3 pi over 3, but 3 over 3 is really just 1. So that's really 18 over 18. So 5 plus 18 would give us 23 pi over 18. That's just doing common denominator arithmetic there with the fractions. If you need to slow that down and rework it or something, that's fine. That's so far as k is 3. Now, the question is, are we still within one wrap of the circle? Well, remember, one full circle is, we're looking at from 0 all the way around to 2 pi. So are we within or less than 2 pi? Yeah, 23 over 18 is less than 2. And you can just do some quick arithmetic to check on that. So let's keep going. What about when k is 4? Well, when k is 4, we're looking at 5 pi over 18, our first term, plus 4 pi over 3. But again, with a common denominator, I'd be multiplying top and bottom by 6 to get a common denominator of 18 for these two terms. This would give us 24 pi over 18. If I put those together on top, I have 5 pi plus 24 pi. That's 29 pi over 18. That's still less than 2. 2 would be 36 over 18, right? So we're getting there, but not quite there yet. In fact, we're going to have to add a little bit of space to keep this going. But you can see how this is going. We're trying to extend and get all of these values until we get through to 2 pi, as the second part of this question is requesting. So what about when k is 5? Let's check this. We'd have 5 pi over 18 plus, it'd be 5 pi over 3 if k is 5. But again, to get a common denominator, I'll multiply top and bottom by 6 there. That would give me 35 pi over 18, which must be the last one. Can you think about why? Because look at 35 over 18 is pretty close to 2. What's 2? It's 36 over 18. If I go one more, if I let k be one bigger and add pi over 3 to this, there's no way it's going to stay within 2 pi. So that certainly would be all of them to represent the full set of solutions between 0 and 2 pi. So let's mark these. We got 5 pi over 18, 11 pi over 18, 17 pi over 18, 23 pi over 18, 29 pi over 18, and 35 pi over 18. All done with our formula and just plugging in different values of k as we went. All right, for our fourth example, we want to find all solutions, then find the solutions in the interval 0 to 2 pi, kind of like we were just doing in the previous problem. But of course, now we're given a different equation. This time the equation is, on the left side, 2 sine of theta over 3 plus square root of 3, and that's equal to 0. I'm going to write this down and say it again. So it's 2 times the sine of, the input for this sine is theta over 3. So the dividing by 3 is going on inside the input for the sine function. So we got 2 sine of theta over 3, close parentheses after that. And then we have plus square root of 3, and then that equals 0. Now, in order to solve this one, we're going to start by trying to isolate the trig function as we've been doing. So we'll begin by subtracting the square root of 3 from both sides. Of course, that'll leave us with 2 times the sine of the quantity square root of, so sine of the quantity theta over 3. And then that's just equal to negative square root of 3 since we subtracted that on both sides. If we now divide by 2 on both sides, we're working on, remember, getting the trig function alone first. This gives us sine of the quantity theta over 3 on the left side. That equals negative root 3 over 2 on the right side. So we want to figure out where this occurs on the unit circle, this negative root 3 over 2. Yes, we have a multiple angle inside our trig function, the theta over 3. Or you could say it's a fraction of an angle. And we'll deal with that next, but we first have to identify where we even are on this unit circle. So I'm going to draw one, and then let's recall where sine values are negative root 3 over 2. So sine's negative in quadrants 3 and 4, and then root 3 over 2 would be the ones that are closest to the y-axis. If you think of like the 3 special places, negative root 3 over 2 for sine would be on the places in quadrants 3 and 4 that are closest to the y-axis. So you could think of it as if you're starting from the normal starting place of 1, 0, then we're talking about going all the way around into quadrant 3. To get there, that would be a place on the unit circle known as 4 pi over 3. And then the second one would be 5 pi over 3. This is just going back to our unit circle values. If you were to extend around to these two places, right? And that's what we have to know. We have to know kind of like the first solution within one circle that we can use as the beginning of our expression for all the infinite solutions. And then we'll find only the ones within one wrap as stated. So to put this in for a value of theta over 3, remember that's the value we were given as the input. It's really a third of theta. What we know is whatever that is, it's got to equal these two special places we just found as at least the starting point. So we'll say theta over 3 equals 4 pi over 3. That was the first spot we would have come to. But then you could say plus, and then we could use the period of sine, since that's our function here, 2k pi. We've seen that going on by now, right? And we can also recognize that these two solutions are not going to overlap each other. Like you can't start at one, add a lap, and hit the other one in so doing, which means we're going to need to represent both. So we have theta over 3 also then equal to 5 pi over 3 plus 2k pi, again, where k is an integer value. Now, we want to solve for theta, not just theta over 3. So what we'll do, like we saw previously, is multiply both sides of these expressions or these equations by 3 in both cases for our solutions. If we do that, we end up with, in the first case, theta equals, if I multiply by 3, the 3's cancel, giving us just theta by itself. But then also on the right side, if I distribute the 3 into those two terms, 3 times 4/3 is just 4, so we got 4 pi, and then plus 3 times 2k pi would be, well, 6k pi. That would be our first solution. For the second one, same kind of things happening, except we'll say theta equals, and on the right side we'll have 5 pi plus 6k pi. Now, those are the ways we could represent all the infinitely many solutions to this equation for theta, because remember, with this periodic nature, the k just keeps incrementing up or down as an integer, and you keep getting multiple solutions. It goes on forever. Now, the second part of this said to find the solutions in the interval 0 to 2 pi. Well, think about this for a second. What if k was equal to 0? In that case, our solutions, using our two formulas that we already established, if you plug in 0 for k, the second terms disappear. That would mean you have 4 pi for the first and 5 pi for the second. Just plugging in 0 for these k's would disappear, giving us only the first term in each of those two equations or formulas to find theta, right? Well, 4 pi and 5 pi are already not in bounds between 0 and 2 pi as requested, so those are out of bounds. Maybe we could get our way back in there, though, if we use something else. Like, if those are way too big, why don't we try, what if k is equal to -1? Maybe this will make it smaller enough to fit within one circle or one wrap of the circle. If k is -1, again, plug those back in to our own little formulas that we've made in the first part of our answer. That means you're getting 4 pi minus 6 pi for the first one. Well, that's -2 pi. And then for the second one, you'd have 5 pi minus 6 pi. That's -pi. Those are both too small. So what we found here is that when k is 0, like if we could eliminate k from this by making it 0, and so that the factor including it disappears, we're already out of bounds if you're trying to look for one wrap of the circle between 0 and 2 pi. So we have no solution there. But those were because they were too big, right? They're bigger than 2 pi. Well, then we went one smaller, like, well, what if k is -1? Well, but then those results are less than 0, which means those don't work either. So we could say there are none. There are no solutions in the interval 0 to 2 pi. Okay, moving on to the next one. Number 5 says as follows. Find all solutions, then the solutions in the interval. So same kind of problem here. This one wants us to find solutions in the interval 0 to 2 pi, just like before. Here's our equation this time. It's given as secant theta minus tangent theta equals cosine theta. Now for this one, I'm going to start by copying down the equation given, except I'm going to rewrite it in its equivalent form, knowing that, for example, secant is 1 over cosine. So we're going to write that first term as 1 over cosine instead of just secant theta. So we have 1 over cosine theta minus, then we have tangent theta given next. We're going to write that as sine theta over cosine theta, because again, that's the definition of tangent theta. And that's equal to cosine theta, which we'll just copy down as given. Now, why would we do it this way? Well, I think we want to observe a nice strategy here, which is we're allowed to multiply both sides of a trig equation by a trig expression. So I'm going to multiply both sides by cosine theta, motivated by the fact that my denominators are both cosine theta on the left side, which means this would clear the fractions. You could say it that way. You might have seen that in algebra, but with numbers instead of trig functions. We're just going to clear the fractions on this. If I distribute the cosine theta to both terms on the left side, I had 1 over cosine. Well, cosine times that would be just 1. And then the second term was sine over cosine. If I multiply that by cosine, I would have just sine theta. The cosines would cancel, cosine theta on top and bottom. And then on the right side, I'd have cosine theta times cosine theta, which of course is cosine squared theta. We're trying to solve this equation, and let's remember everything we've already been doing with equation solving. Notice we have a situation where there's a sine and there's a cosine. They're different trig functions. The cosine is squared, but the sine is not. You may recall that it's ideal probably to be able to factor something like this, as we've seen before. But to do that, you're going to have to get something that looks somewhat quadratic, which means you're going to have a squared and then a single of the same function, not different ones like this. So what we might want to do is use an identity to replace cosine squared theta with something that involves a sine theta, right? That's our question. Can I rewrite cosine squared theta in a way that involves sine theta? Because if so, we might be able to get everything in terms of sine and then go that route with the factoring. So let's bring back our cosine squared identities, actually any identities we have. You may recall that the Pythagorean identity even will do this. So we know, and let me just recall this on the side here. recall, sine squared theta plus cosine squared theta equals 1, which means if you were to solve that for cosine, then you could get the following. I'm going to rewrite our entire equation here. We had 1 minus sine theta on the left side. I'm going to keep that. On the right side, instead of cosine squared, I'm going to solve the Pythagorean identity for cosine squared, which would involve moving the sine squared to the other side. That means cosine squared would be 1 minus sine squared theta. So what we have now is a situation where we have only sine trig functions. One of them is squared, one of them is not. This seems like a recipe for some factoring. To do so, let's get the squared variable positive. It's usually a good strategy to do that, and I'll move it over to do so by adding sine squared theta to both sides. Of course, then we'll have to subtract 1 from both sides to bring everything over. So let's do this. The right side will cancel out to nothing. The left side will have a sine squared theta that's positive. We'll keep that over there. That's the one we just added over there. Then it will have a minus sine theta that was already there. And then we had a plus 1, minus 1. Those will actually just cancel. So we're looking at sine squared theta minus sine theta equals 0 as our overall equation, or at least as it stands currently. You'll notice here, it turned out not to be quite quadratic, but more just like a GCF kind of factoring. There's a multiple of, or there's a factor of sine theta in each of these terms. If we factor out a sine theta, then I would be left behind there with sine theta minus 1. So we got sine theta times, in parentheses after it, sine theta minus 1, and then that's equal to 0. And now we're using the zero product property. This is good news. We're used to using, or like using this if we can. So this means that the first factor, sine theta, could be 0, or the second factor, sine theta minus 1, could be 0. So let's think about this. Where is sine theta 0? Well, bring the unit circle back out. Sine theta is 0 on the left and right sides, where the y-coordinate is 0. That would be known as theta being 0 or pi. For the second equation we have, the sine theta minus 1 equals 0. If we add 1 to both sides, we'll get sine theta equals 1. Where does that occur? Of course, at the very top. That would be where theta is pi over 2. Now let's add one more thing I should have noted back here. When we cleared the fractions by multiplying by cosine, in that case, we have to check for extraneous. I'm going to add this as an extra note. So must check if multiplying by a trig function on both sides. So we've seen this a couple of cases where this applies. If you're squaring both sides, got to check. If you're multiplying both sides of an equation by a trig function, you're also going to have to check. What's interesting here is that pi over 2 becomes a problem. Think about this. One of our answers for theta we got was pi over 2. But pi over 2, when plugged back in, which is exactly what it means to check, will give you division by 0, because the cosine of pi over 2 is 0. So that's a problem. In fact, let me color coordinate this a little bit better here. This answer of pi over 2, if checked by plugging it all the way back in, this would cause division by 0. Because you're dividing in the original equation, you really have a secant, which is 1 over cosine, but cosine of pi over 2 is 0, so that'd be 1 over 0. So because of that, we have to exclude it as extraneous. So we're showing our work for that check even, which means the other solutions we got are where we want to stay, at 0 and pi. If we now seek to represent our solutions to finish off this problem, we'll say the following. Theta could equal, we have them that we found from our first branch much earlier here. Theta would be 0 plus 2k pi, or theta would be pi plus 2k pi. Those are using the two original solutions we got. If you put all of that together, then that's like saying 0, 2 pi, 4 pi, 6 pi, and so on. The first one will give you all the even multiples of pi. The second one will do so, but starting from 1 pi, which means you're really having, it's 1 pi plus 2 pi, which is 3 pi, but then you keep adding 2, so it's 3 pi, 5 pi. So this would be, the first one is really all the even multiples of pi. The second solution set is all the odd multiples of pi, which means you're ending up with all multiples of pi. So altogether, we could say that our solution could be theta equals k times pi, because that accounts for the even and the odd. 1 pi, 2 pi, 3 pi, 4 pi, and so on, going on forever. Positive or negative values for k as an integer. Now for the second part of this, where we want the solutions in the interval 0 to 2 pi, notice the boundaries of that interval given. So let's note this here. We'll say it out of space. Oh, sorry, I'll squeeze it in here. So in the closed at 0 but open at 2 pi interval, so bracket around 0, parenthesis around 2 pi, that's just interval notation. It means we're including 0, but we're not excluding, or we're not including 2 pi and the boundary there. So in that interval, we could say theta equals, well, if k times pi is the way we get any of our values for any integer k, then what if k is 0? Well, then that would be 0. So that works. And then what if k is 1? That would be pi, theta equals pi. That works. If k is 2, going the next integer up, then you're at 2 pi. But remember, we're not actually including 2 pi because of this closed, this open boundary interval here. So that means theta is only within that given interval from 0 to 2 pi when it's 0 or pi, which fit within the definition we just gave above. All right, number 6. Our next example says this: find all solutions, then find the solutions in the interval 0 to 2 pi. Same instructions as previously here, but now the equation is different. It's given as 3 tangent cubed theta minus 3 tangent squared theta minus tangent theta plus 1 equals 0. Now, I'm going to suggest that we recall some of our factoring here. So this is back from algebra. There's something called factor by grouping. And when you have this number of terms, it's a good method to use. So by grouping, what I mean is this: I'm going to group the first 2 terms and the last 2 terms, so out of the 4 that we have. And by grouping, I'm just going to underline them. And then I'm going to factor the GCF out of each group. So for the first group, which was now 3 tangent cubed theta minus 3 tangent squared theta, notice in common to both of those terms would be a 3 tangent squared theta. That would be like the greatest common factor. Then if I were to factor that out of those 2 terms only, after factoring out the 3 tangent squared theta as the GCF from those first 2 terms, really I'm calling that my first group here, we would be leaving behind a tangent theta minus 1. And you can double check that by distributing the 3 tangent squared theta into those terms, and you better get the original group, that is those first 2 terms in our equation. So that should do it. Then we keep the sign between the groups as is. That was the minus sign. Just bring it down between the groups and then look for what's common to the next group, which you'll notice isn't very much except 1, which we're going to now call a negative 1 because of the negative sign that's between the groups. So if I factor a 1 out of those second 2 terms in the second group there, really it's a negative 1. That would leave behind a tangent theta and then minus 1. Okay, so that's where it'll end, all equal to 0. Now, as you'll recall from factoring by grouping, it's a good sign if the parentheses that you've just created by factoring each group match, and they do. So what that means is we can factor that matching set of parentheses out in front. I'm just going to write that as tangent theta minus 1 in parentheses. That's just what was common at that previous step. And then what that would be leaving behind if we factor that out is what would be in front of those two terms previously. So we're talking about the 3 tangent squared theta and the minus 1. So those will go in a set of parentheses following 3 tangent squared theta minus 1, and that's all equal to 0. So what we have now is a place where we can use the zero product property. That's good news. We have a product of two factors equal to 0, which means we can set each one to 0. So this means tangent theta would equal 1 if I just subtract 1 from both sides of that equal to 0, that first factor. Second factor, similarly, add 1, divide by 3, we'll get tangent squared theta equals positive 1/3. And then, of course, if you take the square root of both sides of that second equation, we'll end up with tangent theta equals, it will be plus or minus, and then root 3 over 3 if we're going to rationalize and make it look familiar to us for the unit circle. All right, so we're looking to solve for theta in this, and then, of course, find the solutions in one full circle as given in our instructions. The first set has tangent theta equal to 1. What we got to do is remember where that occurs on the unit circle. So again, go back and refresh or look at that unit circle again. Hopefully you have your tangent values on there. Tangent is positive in quadrants 1 and 3, and it's equal to 1 at all the midpoints of those arcs in those quadrants. So we could say theta would be pi over 4, that's the quadrant 1 value, and then 5 pi over 4 would be the quadrant 3 value. Now where tangent theta equals plus or minus square root of 3 over 3, go back again at the unit circle and look at it. This would be all the places closest to the x-axis above or below it. So this would be where theta is equal to, we'd have pi over 6 in quadrant 1, that would be where it's positive. We'd have 5 pi over 6 in quadrant 2, it'd be negative there. We'd have 7 pi over 6 in quadrant 3, it'd be positive there. And then we'd have, 11 pi over 6 in quadrant 4, where it'd be negative. So we're just finding the places where it's either equal to plus or minus, positive or negative, root 3 over 3. In fact, all of these values for theta would be our list of solutions we want within one wrap of the circle from 0 to 2 pi. That was our second part. So let me just mark that. They want all the solutions between 0 and 2 pi. That's what we've just listed. Sometimes it's helpful to start there because you're kind of just working your way around the unit circle. But then additionally, we want to know what are the general solutions that we can represent, right? So if we go back to our unit circle, just kind of visualize where all these solutions would be. You'll notice we have multiples of 6 and 1/6 and multiples of 1/4 in various ways. So 1/6, the multiples of 6 would be like the pi over 6. And then if the period of tangent is pi, then I can keep adding or subtracting pi from that, but that would cover a lot of the other values, right? So if I start at pi over 6 and add pi, that's a half circle. Notice that would take us to the opposite side of the circle. That's known as 7 pi over 6. And then you can keep going back and forth with that, but that wouldn't cover quite everything we need. So we're also going to have to use these multiples of 4s, and let's summarize the whole thing in this way. So we'll say for our final answer, theta equals pi over 6, that's the starting place, plus k times pi. So you're starting at the first place and then adding multiples of pi above or below it to catch all the others. I should say some of the others. So pi over 6 plus k pi will cover pi over 6. It will cover 7 pi over 6 because that's like saying 1 over 6 plus 6 over 6 if k is 1. So that'll give us 7 pi over 6. But we have to be able to account for all of these. Notice some of the others are going to have to start with a different initial value because of this pi over 4 we had from our first solution set. So we're also going to have to say that theta equals pi over 4 plus k pi, again, period of tangent being k. And that will take care of, let's find out. If we go back and highlight those, we have pi over 4 plus k pi. That will account for pi over 4. If k is 1, that's like 4 over 4 pi, which would give us the 5/4. So that takes care of those two. Notice there's a couple left, though, that we haven't quite accounted for yet. That would be the 5 pi over 6 or the 11 pi over 6. But if you go back to the unit circle to visualize, 5 pi over 6, remember that's quadrant 2. 5 pi over 6 is over there. And then symmetrically across from it is 11 pi over 6. So actually those will play nicely together. We'll be able to say theta equals, I'll pick the lower one, the 5 pi over 6, and I'll just say plus k pi, because if k is 1, then 5 pi over 6 plus 1 pi, which is 6 pi over 6, gives us the other one. So there we go. We'll be able to account for all the others in that same way. So we'll say that when theta is equal to 5 pi over 6 plus k pi, that accounts for 5 pi over 6 and 11 pi over 6. Okay, there we have it. So we've answered both things. We found all the general solutions with our k formulas, and we found all the solutions that are within one circle, 0 to 2 pi. All right, our next example, number 7, says this: use an addition or subtraction formula, so they're giving us a bit of a hint there, to simplify the equation, then find all solutions in the interval 0 to 2 pi, and the equation given is as follows: cosine theta cosine 3 theta minus sine theta sine 3 theta equals 0. Now, if your formulas are fresh in your memory or you've been writing them out a lot lately, you may start to recognize what they're giving you. Plus, there's a major hint where it says to use an addition or subtraction formula. Specifically, let's recall that cosine of s plus t, in parentheses, equals cosine s cosine t minus sine s sine t. And the reason this might be useful is, well, hopefully it's recognizable that the right side of this identity, at least the way I've written it here, there's no left or right side officially if it's an equation, either way or either direction's okay, but the right side, the way I've written it, matches up with the left side of the equation given. That is, the right side I wrote was cosine s cosine t minus sine s sine t. The left side of the equation given is cosine theta cosine 3 theta minus sine theta sine 3 theta. In that way, we should be able to match up what the s and the t are here. So we could say, for example, s, at least the way it's used in the way we've written out our identities, s would be the first input, which is just the theta, and then the t, which would be the second input, would be the 3 theta. When I say first and second, I'm referring to the order in which they're given on the right side of our identity, the way we had written it when we did the addition and subtraction formula. Okay, so if that's the case, then using the identity, we can just simply move backwards with it. Or at least it kind of feels like backwards, but we're now moving from the right side to the left side of this identity, which means what we have is really equivalent to cosine of, in our case, theta plus 3 theta. That's the s for theta and the t, like the 3 theta. So the left side of the equation given is really just equal to cosine of, in parentheses after that, theta plus 3 theta. So all that must equal 0. Well, this is getting simpler, right? Now we could say, if we combine like terms inside the parentheses, this really means cosine of 4 theta, that's the theta plus 3 theta. Cosine 4 theta equals 0. Well, now it's just back to some of the multiple angle stuff we've been doing, right? We know where cosine is 0. Just pull out your unit circle. And remember, cosine is 0. If cosine is x, it's 0 on the top and the bottom of the circle, which means this is where the angle for us, given as 4 theta, would be equal to, on top, pi over 2, or on the bottom, we'd say 4 theta equals 3 pi over 2. And like we've done already with some of these, we're going to solve for theta by dividing both sides by 4. So if we have 4 theta equals pi over 2, and I divide or I should say multiply by 1/4 on both sides. Right, we've seen this already going on. That means I have theta equals pi over 8. It was pi over 2, but I'm multiplying that by 1/4, so pi over 8 it is. If I go to the second solution we had, where 4 theta equals 3 pi over 2, those are all the places at the bottom of the unit circle. Again, dividing both sides by 4 would yield then theta equals 3 pi over 8. That's just multiplying both sides of that by 1/4. Which gives us a couple interesting values. We have theta equal to, let's start listing these. We have pi over 8, and then we have 3 pi over 8. Now let's recall something else very important. If we go way back to when we did transformations, when you take something like cosine of 4 pi, remember the period gets adjusted when we do the horizontal stretching like that with that 4. We said the period equals 2 pi, the regular period, over b being the value, in this case, 4 in front of the theta. So let me just say recall, this is from much earlier topics. Period equals 2 pi over b, 2 pi being the pure or regular period of cosine in this case. So for us, that would be like 2 pi over 4, since there's a 4 in front of the theta here, which would be pi over 2. So we can use this to string out more solutions here. I'm going to write, instead of our period being pi over 2, I'm going to write it in a common denominator of 8, since that's what we're working with right now. Really, pi over 2 is 4 pi over 8. And since we have an 8 as our denominator, I'm just going to kind of note that there. So if I tried to string together more solutions, then notice I could take the first solution of pi over 8. If I added 4 pi over 8 to it, that is the period we have, 4 pi over 8, that would give us 5 pi over 8. So let me indicate here, we're simply adding the period, which is 4 pi over 8. If I do the same thing with the next, or the original next value here, the 3 pi over 8, 3 plus 4 being 7, this will give us 7 pi over 8. And we can just keep this list going. We're adding the period of 4 pi over 8 to the values we have to generate the next ones. The question is, how long do we go with this list, right? Well, we were given an original boundary here, right? The interval set from 0 to 2 pi for theta. So we're looking at now theta. We've already solved for just a single theta. We're not using 4 theta anymore. And for theta, we want to go from 0 to 2 pi, not including 2 pi, but including 0. So we basically need to keep counting up until we get there, but let's save ourselves a little headache. Can we find the pattern here? Notice what you're doing in the numerators. The denominators are all 8s for these, right? But notice the numerators. It's 1 pi, 3 pi, 5 pi, 7 pi. Are you catching the pattern? These are just odd numbers. So then it'd be 9 pi over 8. And then you guessed it, 11 pi over 8. How do we know when we're done? Well, we're trying to get all the way up until 2 pi, but not past it. So 2 pi would be 16 pi over 8. So let's keep going. So we had 11 pi over 8, 13 pi over 8, 15 pi over 8. Again, I'm just adding up the odd numbers, multiples of pi in the numerators. They're all over 8 for the denominators. And notice we're here because the next one would be 17 pi over 8, but that's more than 2. 2 being 16 pi over 8. So we stop right there. This would be then all the values between 0 and 2 pi that we'd want to list. And that's all they asked for. Now, you could arguably try to get the general form for this, for like in terms of k as we've been doing. If you wanted to, we could start, notice the pattern. You're starting with the first one being just pi over 8. And then we're adding a consistent amount to it each time. We're adding 2 pi over 8. So it's really just pi over 8 plus pi over 4 times k. Again, where k is an integer. But we're adding, how do we know we're adding pi over 4k? Because that's what's going on. From one to the next in this whole list, they all go up by 2 pi over 8, right? It's 1, 3, 5, 7, 9. You're adding 2 to the numerators. The denominators are all 8. That's 2 over 8, also known as 1 over 4. So if I just keep adding 1 over 4 pi to this, any multiple of it, any k multiple, this should generate all the solutions going on. The first list is only the ones between 0 and 2 pi that was asked for in this problem. All right, let's keep rolling. I know there's a lot of material in this one. We're almost there. Two more examples. Number 8 says use a double or half angle formula, so they're giving us a little hint here, to solve the equation in the interval 0 to 2 pi, excluding 2 pi. And the equation given is cosine 2 theta plus cosine theta equals 2. Now, you'll recall or notice right away that we have only cosines, but we also have a double angle expression and a hint that we're supposed to use some kind of double or half angle formula here, right? So look back and recall all your options for cosine 2 theta and then think ahead a little bit. This is the one that has 3 options, you'll recall if you look back. And we'd like to get something that we can possibly factor. So I have a single cosine term is my second term. Is there a way to get a squared cosine term for the first one? Can I turn a cosine 2 theta into a cosine squared? The answer is yes. And actually, we also would like to have only one type of trig function. So if I can keep a cosine squared but not a sine squared, that's probably ideal. Well, it turns out we have an identity for that. So cosine 2 theta, turns out, is the same thing as 2 cosine squared theta minus 1. So we're just replacing the cosine 2 theta as our first term with 2 cosine squared minus 1. That's just from an identity. And then we'll carry on. We have then plus cosine theta, our second term, and then that's equal to 2. Well, you'll start to recognize here we have a squared cosine, a single cosine. We should probably get this into a factoring form, or at least try. And to do that, I want everything on one side. I'm going to bring this 2 over by subtracting it. So let's see, this will give us 2 cosine squared theta as our highest power term. Then I'll go in descending order. So next I'll say plus cosine theta. There's the single cosine term we had. If I subtract 2 from both sides, I'll really have a minus 3 because I had the minus 1, but I'm subtracting 2 from both sides. So minus 3 it is. Okay, we're putting this all together, giving us this now factorable trinomial looking thing. We have 2 cosine squared theta plus cosine theta minus 3 equals 0. Can we factor it? Well, I don't know. Let's put our factoring hat on and see. Let's try a 2 cosine theta and then a cosine theta in the front of each set of parentheses here. And then can we think of 2 values which after them would multiply to get a negative 3? And so that the outers and inners, when we combine them, will give us a positive 1 when we do the guess and check. So let's try it. I'm going to put, let's see, maybe a minus 1 after the cosine, and maybe a plus 3 after the 2 cosine theta. So let's check this. First times first would be 2 cosine theta times cosine theta. That's 2 cosine squared theta. That's what we want for the first term. Got it. Outer times outer would be a negative 2 cosine theta. Inner times inner would be a plus 3 cosine theta. Well, negative 2 plus 3 is plus 1, what we want in the middle. And then last times last would give us the negative 3 we want for that third term. Okay, so we've got it. Now we also have the zero product property in play. We have the product of two things equal to 0. That means the first factor could be 0. So 2 cosine theta plus 3 could be 0, or cosine theta minus 1, the second factor, that could be 0 as well. Again, just using the zero product property. This first equation gives us then cosine theta equals, if I subtract 3 and divide by 2, cosine theta equals negative 3 over 2. But negative 3 over 2 is really negative 1.5. Cosine can't be that big. It can only get as big as 1, or negative, small as negative 1. So that's going to give us nothing. The other side was cosine theta minus 1 equals 0. If I add 1 to both sides, that gives us cosine equals 1. That's not a problem. We know where that is. That's on the right side of the unit circle, where the x-coordinate is 1. And so, of course, theta would be 0 over there. Or if you take the period in this case, let's be careful here. We have cosine 2 theta, which we turned into a cosine squared theta. Okay, the point here is that the period of this original function would be 2 pi. If I add that to my current value of 0, my next solution is 2 pi, but that's not actually in the interval because of the open boundary that does not include 2 pi. So we actually won't even include that and simply say 0 is the only value that's fitting within 0 to 2 pi. Okay, last example, I promise. Here we go. Number 9 says use a sum to product formula to solve the equation given as sine theta plus sine 3 theta equals 0. Now, you'll recall, probably gladly, that you did not have to memorize the sum to product formulas. So you'll be provided these if needed on an exam or something, but take a look back at them and see what might be involved for this equation. We have sine theta plus sine 3 theta. If you look carefully at the options that involve a sum of sine functions, you'll recall one that might be relevant. And that is, we said sine of x plus sine of y equals 2 times the sine of x plus y over 2 times the cosine of x minus y over 2. Okay, so that's just one of those identities or formulas we have that you don't have to memorize, but do have to know how to use. So here we go. Now we're saying that x, at least as it is in the given formula, x for us is like theta, and then y for us, the second input here, is like 3 theta. So all we have to do is plug these in accordingly. So we'll say sine theta plus sine 3 theta equals, here we go, it's going to be 2 times the sine of, the first input is x plus y over 2. Well, that would be theta plus 3 theta, also known as 4 theta. I'll just put it that way, 4 theta over 2. And then the cosine of x minus y, well, the order matters here, so that'd be theta minus 3 theta. That's also known as negative 2 theta over 2. Now, before I get lost running away on this, I should go back and indicate, right? We're saying that the original equation's left side, sine theta plus sine 3 theta, that's what we're now saying is equal to what we currently wrote, which is 2 sine of 4 theta over 2 cosine of negative 2 theta over 2. So we're going to simplify that, but I don't want to get lost from the fact that we really do have all of this equal to 0. So I'm going to recopy this and do just that. I'll say 2 sine of, we have 4 theta over 2, also known as 2 theta, times the cosine of, it's negative 2 theta over 2, or in other words, just negative theta, and that's equal to 0. We're now at a place where we can use the zero product property, perhaps with some more identities as well. Furthermore, anything with a variable matters for the zero product property, but a constant factor like 2 does not get involved because, of course, 2 cannot be 0. So we just take the variable factors, which would include the sine of 2 theta, and say that could equal 0 as part of our zero product. Or the second variable factor, this was cosine of negative theta. Now remember the negative identities here? We could just say that's the same thing as cosine theta. So I'll just say here negative identity. Negative identity means that cosine of negative theta is really the same thing as just cosine theta. That could equal 0 as well. All right, so we're concerned about where this might happen. For sine, we're saying that 2 theta would equal whatever it takes for sine to be 0. Well, that would be either 0 or pi. Moving over, where does cosine equal 0? Well, that would be at pi over 2 or 3 pi over 2. If we put this all together, let's think of it this way. So 0 and pi, those are the places of the solutions for our left side, our sine of 2 theta equals 0. That would be the left and right side of our unit circle. Let's just visualize this for a second. That's left side and right side, 0 and pi. For the second factor, in our zero product, where cosine theta equals 0, we had pi over 2 and 3 pi over 2. Well, that's the top and bottom of the unit circle, which means theta is a solution when it's at any of those places. Well, if we're going to summarize this going on forever with the periodic property, or just kind of using the k value here to represent any solution, then what we could say is that theta could be any multiple of all of those quarters of the circle. How much is a quarter circle? Well, it's pi over 2. So we could summarize by saying theta is really just k times pi over 2, again, for k being an integer value denoted with a script z typically. So that's the idea, where it'll count for all the different solutions that we could use or represent going on forever in any direction.